exactly is going to be doing the movement. It's going to be the elbow, right? So the first part of the question was just pretty much things that we did on angular acceleration, and we remember we solved that, right? We solved that. So then we now got the second part of the question, which then says, which is B, and says calculate the moment of inertia of the system consisting of the forearm and the ball. So here now you're trying to calculate the what? The moment of inertia for the what? For the forearm and the ball. So then, uh, for this question again, so you have to start looking at, remember, whenever you are calculating the what's this, the moment of inertia, you always have to look at a radius. Okay, so you look at the mass of something and the radius of something. So what is that radius? That radius is going to be the or rather the distance from the axis of rotation to where the ball was, right? So in this case, since the movement that this person is going to make is going to be at the elbow, so we can take the elbow to be our point of what? We can take the elbow to be our point of rotation. So what then this entails is that at this particular point at the elbow, that's where the rotations are going to be happening. And so we can take the length of this elbow, of this forearm, from the forearm to the center of the ball, which was given to be 0.35 meters. This is going to be what? Our radius. Think of it that way, right? So once we've done that, now we know that this particular system consists of what? Consists of two things. Okay, it consists of two things. It consists of the ball and also consists the of the forearm itself, right? So we have to, because they're saying find the sorry, calculate the moment of inertia of the system consisting of the forearm and the ball. So meaning that we have to find, or rather calculate the moment of inertia for the system consisting of the forearm and for the ball. So let's find the moment of inertia for the ball and the moment of inertia for the forearm. We add the two, that will be the moment of inertia for the system. So I hope everyone has gotten that. So let's now begin working this. So we know that the length of the forearm, it was 0.35 meters, and then so this is the elbow, right? And then the ball is here. So it's saying it's yeah, so it's there, right? Then we know that the mass of this, the mass of the of the forearm, so mass of the forearm is 1.5 kg. They've told us in the question. Then the mass of the ball is what? It's 0.15 kg. So then what we're going to do is the formula for moment of inertia is this, which is going to be okay, let's just designate what we are talking about. So ball, okay, so since ball, so we are going to say mass times r squared. So the mass is going to be 0.15 kg. Then the radius, like again, remember I said we are using the length of the arm and I explained why. Okay, let me write that bracket properly. So the answer is going to be that, right? So remember, but we've been asked to find for the system. So we now have to find for the forearm, the mass, so that's the mass. Then we are going to have, now remember, and something to take note of is that for a ball, this is just the formula for it, right? For the moment of inertia. But when it comes to the forearm, remember this diagram that I told you to, these things that I asked you to know, not to memorize. So you see, between these two things, between the one on the left and the one on the right, which one is the formula for us? You see that because the axis of rotation, we're taking it as being the elbow. It means that it's we can take the forearm to be like a rod which is rotating through the end, okay? Of which our end in this case is what? Is our elbow. So so it's not just going to be mass per r squared, but it's also going to be 1 over 3. So I hope that we've taken note of that, right? So please, people make mistakes like that. Okay, so please don't make a mistake like that. So last time I said you have to know those. Okay, so once you've done this, then you now find your answer. Yes. Okay, so what I said about the 1 over 3 is when you look at the question that we had, right? So we are taking where where I'm putting the star there. That's what we are taking to be our axis of rotation, right? And so when you remember that for different shapes, you are going to have different standardized what? Moment of inertia, right? So you see that's the standardized one. So then you have to ask yourself to say, from the question that we have, which one fits the picture that we are having? So first of all, you can look at the forearm. The forearm isn't a cylinder, the forearm isn't a sphere, but you can picture it as a rod, okay? As a rod, isn't it? Like, so we are now focusing on last uh the last row, isn't it? Now, in this last row, we then ask ourselves to say, in the question that we are dealing with, where is our axis of rotation? Is it through the center of the rod, or is it through the end of the rod? And we see that it's towards the end of the rod, because remember, in this question we are taking the elbow point, huh? So remember, we are taking the elbow point, this point, to be the axis of what? To be our axis of rate. So meaning that it's the same as we are saying this is the same as that, because we are taking this end and we are making it as this end, and then this end is just a rod like that, the way that place is a rod. So we see that this one is the one that fits our picture. Therefore, the moment of inertia formula we are going to use, we are going to use this. Of course, it's going more accurately, we could say L for length, but anyway, we could use radius, it's fine. But you've gotten the point, right? Okay, okay, welcome. So that's about it. So then we've gotten those two answers, but remember the question was telling us to find the what? To find the moment of inertia of the system. Okay, so to find the moment of inertia of the system, so we're just going to add the moment of inertia for the ball plus moment of inertia of form. Then, so you're just basically adding those two, then you're going to have this. So you see, the key thing is not to memorize, it's just to understand what's happening and you picture it to say, okay, the shape that I'm having, what is it really, uh, close to, okay? So that's something that's important to take note of. Okay, so having done that, uh, we can then, yeah. So basically, okay, yeah. I think there's another question, right? Yeah. Then the third question is find the torque exerted on the system that results in the angular acceleration found in part A. Okay, so what they're asking us, so we found the moment of inertia, that was B. A, we answered it last week. So then, with what we are having here, They are telling us to say calculate the torque exerted on the system that results in the angular acceleration found in part 1. So we we derived a certain formula last week, which was saying torque is equals to moment of inertia times angular acceleration. But in this case, it's going to be angular of so it's going to be moment of inertia of the system times the what? Times the angular acceleration. So why are we saying system? Because remember, we are talking about the torque exerted on the system. So we can't use just the torque for the forearm or the torque for the. So some questions may not even ask you to find the moment of inertia of the system, and then most people will make the mistake of just using the moment of inertia just for the ball or for the forearm alone. But the question is saying the moment the find the torque exerted on the system. Okay, so that's the thing. So we know that the torque there, or rather the moment of inertia. Sorry, let me write that. Then we remember the angular acceleration that we found last week. You can check last week's video for you to revisit it. Then so the torque is going to be 22.8 Newton meter. So that was the torque that was put on. So in yeah, so basically that's how really you handle these questions. Just understand the concepts, look at the question step by step, write a free body diagram, and you'll be set to go. So then let's now look at an interesting question. These questions, huh? Yeah, they usually like these questions. You hardly write an exam without these, huh? So let's go through this question. A solid, uniform, frictionless cylindrical ring of mass m, 3 kg, and radius r, 0.4 meters, is used to draw water from a well. A bucket of mass 2 kg. So remember, the cylindrical wheel, it's this wheel, okay? The one to which the rope has been tied, okay? So let's take note of that. Then a bucket of mass, which is, so that bucket there has got a mass of 2 kg, is attached to a cord that is wrapped around the cylinder. So before I forget, in these kinds of questions, it's very important that you actually zoom your eyes and look at how the rope is tied on that reel that's rotating. Do you know why that's important? It's because that determines whether your torque is clockwise or counterclockwise. That makes sense, right? Okay, so yeah, here's the catch. For this one, you see the rope is like this, right? So meaning that when the bucket goes down, you're going to have a torque which is going to be what? Clockwise, isn't it? So you've got a negative torque. Okay, then there are other questions, and that's why I sent that Shom's book to you on Google Classroom so you can be able to be going through these things. Because those questions are there and they've been answered and explained. So then there's 10 times where they've rotated they've put the rope like this, then it's coming like this, then there is a bucket. So I hope you see that this one here, the torque is what? Is negative. But this one that I've drawn here, the torque is positive. Because the wheel is moving like what? Like that, and the bucket is going like that. For this one, the torque is going like that, and the bucket quite right is going down. So it's very, very important that you analyze how have they tied the rope. How have they tied the rope? Because that's important. Okay. What other point can I want to talk about here? Yeah. So now, again, the other thing why it's important to take note of these things, and the main reason why I'm using this picture, not our board, it's because this picture to be easy for you to really relate with what I'm talking about. So now, the other thing that why it's important to take note how that cable has been wound around this reel. It's because of these two things: and angular acceleration and what, and the normal acceleration or the linear acceleration. So we know that these two have got a relationship, isn't it? So we know that these are related by what? We say angular acceleration is what? It's that's the translational acceleration over r, isn't it? So we have that equation. So now in these questions there is a part where you have to substitute this, but what you plug into what you'll be substituting. And the main reason why I'm explaining these things before we do them is because it will be easier for you when I start doing them. Okay, it will be easier when I start substituting. So that's why I want to do all the explanations here, so that when when we start solving, we just rush through. Okay, not rushing through, but we just go through. So now that's about it. So now one thing you have to take note of is what is going to be the sign of angular acceleration. Okay, it's going to be what? Negative. Why is it negative? Because this thing is moving clockwise. We know that in angular motion, when something moves clockwise, it's negative. Let's then talk now about our linear acceleration. For this one, you are focusing on the bucket. Which direction is the bucket going? It's going down. So meaning your linear acceleration will be what? Negative. So what does this mean? This equation is going to be. This simply means our this equation that I've put in this nice box is going to be the way it is. I hope that makes sense. Then, if this thing was wound around this in this manner, where it's like that, it's like that, then the bucket falls like this. So to solve such questions, check that book that I sent you on Google Classroom. That's where they get exam questions. Anyway, so for this one again, we want to write what will be the angular acceleration, what will be the linear acceleration, and what will be the sign of our lovely equation there. Okay, so what's going to be the sign of our equation there? Is it going to have a negative anywhere? And you see the implications of this. So you see what is going to be our angular. How is this thing moving? This wheel is going to be moving where? Counterclockwise. So meaning what? Angular acceleration is going to be positive. Okay, then the linear acceleration, the bucket is still going downwards, so it's going to be negative. So negative, so you see that when you be doing your substitutions, you remember to put a negative. So you can put in, but anyway, the fact is that the thing you'll be substituting will have a negative. So that's why it's very, very important to zoom in and say where is, or rather how is this rope being being wound around this thing that is rotating. So I think that's really, really the thing that's important. The rest of the things we've already covered. Yeah, so without wasting much time, let's just go through the question again. So okay, let's zoom it like that. Yeah. So we've already looked at, yeah. So to a cord that is wrapped around the cylinder, find the tension T in the cord and acceleration A of the bucket. That then B, if the bucket starts from rest at the top of the well and falls for 3 seconds before hitting the water, how far does it fall? So the second one is just basic kinematics, huh? But where the money really is for this topic is finding the tension and the acceleration. Okay, so what's very what I say? 258. Okay. So now, what you want to look at in this case is, like I always say, don't memorize. So let's write the wheel like this, and then so that's the wheel that's rotating. Then we know that so there is weight. So there is the weight of this thing. This particular wheel is going to have a what? It's going to have a mass and going to have a weight. Then to counter this weight, we are going to have a norm. Okay? Then then what then you're having is there is a rope. Okay? So there is a rope. There is a rope. So what is this? Why have I drawn this? It's for you to see that at this point here, at this point, at this point, that's why you're going to have the tension due to the rope. Okay, so there's nothing to memorize there, right? So this rope is going at that point of the wheel is going to have a tension T. So now let's now write it. That's why I need people to see where that was coming from. So here you see there's going to be a what? There's going to be a tension as a result of the rope. So T there, right? So those are really pretty much the that's the free body diagram for the wheel. So now let's now look at the bucket, because also the bucket. So for this bucket, what's really happening on the bucket is this. For the bucket, it's it's being it's got a force which is up, and then it's also has got a weight. Now, what's the force that's up? Remember that the bucket is attached here. Okay, so meaning the upward force on the bucket is what? Is the same tension that's acting on that wheel. So with that free body diagram drawn, is everyone comfortable before we can proceed? Okay, so now what then do we do? We then look at the bucket and say, since the bucket looks a little bit straightforward, so let's go for the bucket. Let's write the so we know that there are no horizontal forces on the bucket, we're only having the vertical ones. So how are we going to write it? So it's going to be T minus mg. So we were just writing the forces, right? So the T is positive because it's facing upward. The weight is downwards because it's negative here because it's downwards. Then it's going to be accelerating, right? This thing is going to be accelerating. So that's our equation. You could call it equation 1. So with this equation 1, we can now leave it there for now. Then what we are now going to focus on now is we are going to focus on this wheel. So what we are going to do now for this wheel is we're going to now write to say what's really happening on this wheel. So what we're going to say, we're going to say uh, the sum of torque is equal to moment of inertia times angular acceleration. We've already discussed that. Then now we know that for this moment of inertia, this particular wheel, how does it look like? It's a solid cylinder. Let me just so you see the way it's looking, huh? It's a solid. Okay, it's a solid. So, but you have yeah. So since it's a solid, it means moment of inertia are you going to use? You are going to use for this one, the one that is a what? A solid disc or a solid cylinder. So you are going to use that one, right? Okay, so meaning where we are at the moment of inertia, we put that capital M, capital M. I'm just going to put capital M and capital R just to differentiate. So that R is the radius from the center to where the tension is. Then we know it's going to be squared. Then we are going to have angular acceleration. Okay, so with this having been done, now there's something interesting about our torque. Then we know that this particular torque, we can actually express it. So in fact, let's do it like this. We know that our torque is going to be negative, right? Because of what we've already discussed. Now don't confuse torque with T. So let me write it fancy so that people can see the difference. So that's not tension, that's torque. So torque, and we've explained why it's negative. So now what we're going to do now is to say this torque that we've calculated, that we've had this equation for, we know that what's providing the torque? The torque there is being provided by what? It's being provided by the tension multiplied by the radius. Okay, so the tension being from the rope that's connected to the bucket, and the radius being the distance from, of course, the center of the wheel. So then meaning we can rewrite this torque, negative torque, by saying negative torque is the same as negative tension times radius is equal to mass of the cylinder, radius, and angular acceleration. Okay, so once you've done this, then we are on the right path. Then what do we do? Since r is common on both sides, we can cancel it off. Okay, so we can cancel it out. Okay, so we are going to have negative tension, then you are going to have half, then you are going to have mass of the wheel, and then you're going to have that. So that's your equation. Now, what really can you do with this equation that can actually make your work easy? You can now realize, say, okay, there, I know what the mass is, right? You know what the mass is, and you know what the radius of that thing is, because they gave us the mass is 3 kg and the radius is 0.4 meters, right? So the only thing that you don't know at this point is your angular what? Your angular acceleration. But then you realize, say, oh no, there's actually a way that I can actually what? There's actually a way that I can actually solve for this. So then, how do you go about it? So what you do in this case is you say, let me use blue so that we don't mix things up. This alpha acceleration. Alpha, oh, sorry, not alpha. Angular acceleration is the same as A over R. Now, many people again make mistakes on this, in that you have to ask yourself, how is this wheel moving? So, is it moving counterclockwise? It's moving clockwise. So, meaning your angular is what? Is negative. Then what about the bucket? It's moving downwards, so that's negative. So if you've got two negative, if you've got a negative on this side and a negative on this side, meaning this is going to be what? It's going to be like this, right? So the equation is not going to have any negative. Now, why is this important? Because there are certain questions depending on how the cable has been wrapped around that wheel. You can actually have where this thing, this expression can be negative, and many people make the mistake of falling into that trick. So don't take it for granted. So having done this, we can now substitute that into our equation. So where we had angular acceleration, we just put a over r. Okay, we know that's going to be a capital R when we put it. Okay, so we do that. That's going to be m r. Then here it's going to be a over r. So we are going to have minus tension. So the r goes. You remain with ma. So mass and acceleration. So then at this point, you then say, okay, so now what now can I do with this expression that I have? Then you now remember the first equation that we came up with. It was like this. Okay. So at this point, you may want to use this equation. Okay. So at this point, you may want to use this equation. So okay, let's do that. Let's do that. Okay. So then what you're going to do, it's so you say, how do you make t the subject of the formula? So making t the subject of the formula, we are going to have that, right? So what you do then, and if you want to make your work easier, since we are solving for acceleration, anyway, no, let's just leave it the way it is. So don't forget that minus sign that's there. Okay, then capital M there, right? So what then do you do to this? If you want, you can multiply through by half by 2 to get rid of that half. You could do that. Yeah, that's something that you could do. Or okay, so that's something you could do. Or you can just say minus g minus that over half of the mass, like that. So can someone just help us compute this? So we are going to have the mass of the bucket. So can just someone help to compute this for us? Oh, sorry. Just pardon me a moment. Sorry. Not yet. There is no way we can solve when that other side has got the acceleration that we don't know. Okay, so there is this acceleration, we don't know what it is, right? So we have to make this come this side, right? Yeah, sorry about that. Okay, yeah, great. Yeah, so we have the acceleration on one side. So to have the acceleration on one side, then we can factor the right hand side. Okay, now we've got an an expression in which we have all the values. For that one, there's no way we could have solved that because we didn't have the a there that was appearing. So that's capital M and small letter that. So can someone just help compute that? Okay, so that's about it. Yeah, so that's basically how you solve for this. So plugging in your values. Okay, so that is going to give you a value of negative 5.60 meters per second squared. So the thing is that we started building from the what? From Newton's laws. Then from Newton's laws, then we actually got to find this. Then since we've been able to find our acceleration here, this simply means that we can actually be able to find our tension from this equation. Okay, so from this equation we can find our and you see that that acceleration is negative, which is what we expect because the bucket is moving downwards. But the tension, because the tension is what's ensuring that the bucket doesn't fall anyhow, so it makes sense that its actually has got a positive value, 8.40 newtons, because it's what's actually ensuring that the bucket doesn't fall anyhow. So that's about it. Then we now go to the last part. So the last part is just a review of kinematics, where they are saying if the bucket starts from rest at the top of the well and falls for 3 seconds before hitting the water, how far does it fall? So there you are just basically using this equation. We are using y because of vertical. So you use that initial velocity plus half acceleration t squared. So they are saying that it's starting from rest. So meaning that here you are going to have 0. Then we've got our acceleration there, which is negative. Then uh, the time they've told us it's 3 seconds, which we have to square. So then we see that actually this fell, it's negative 25.2 meters. This negative just shows that it was falling where? Downwards. That shows that it was falling downwards. Yeah, so that just shows that it was falling downwards. So really, with these questions, is they usually look complex, but once you just understand to assess how was the cable wrapped around the cylinder, once you understand those things, you'll be able to answer these questions without really having to get worried as much. So that's the key thing. Then the other concept now we look at is rotational kinetic energy. So now we know that when an object is rotating, or rather when an object is moving, it's going to have kinetic energy, which is half mass times velocity squared, right? So even in the same sense, when an object is rotating, okay, so you see, mass is analogous to what? Moment of inertia. So you see, that's why this equation has got, so that's why the rotational kinetic energy is going to be half. So the half is going to be the same half. Then the mass is going to be replaced by something that is analogous to mass in the rotational motion, which is what? The moment of inertia. Then the velocity has been substituted for by what? Has been substituted for by the angular velocity there, right? So then what then does this tell us? It then tells us that if you are looking at a mass like the one that is on the far left, what this entails you is that when we try to pick any point on this thing that is rotating, to find the kinetic energy or the rotational kinetic energy, we have to find the kinetic energy of all the points that we are trying to look at, and then we add them, right? But then when we add them, what you realize is that, look at these brackets. You see, those brackets, the sum of the mass of what? Mass times r squared times radius squared. What's in the bracket? That's the formula for moment of inertia, right? Standard formula for moment of inertia. So meaning it's the same as a half times moment of inertia for that particular thing that you are looking at, multiplied by the square of the angular velocity. So here now we have that particular formula that we are looking at. So you can see there on top, which is equation 8.10. So that's basically that. Then we can then relate this with the work energy and things that we discussed. So what did we say? When energy is conserved, remember we said when energy is conserved, meaning when there are no non-conservative forces, meaning when there's no friction and things like that. We know that kinetic energy initial plus we know that potential energy initial, kinetic energy initial is equal to kinetic energy final and potential energy final, right? We did that during work energy and power. So for this one as well, when there's no friction, when there are no non-conservative forces, you see that translational kinetic energy, gravitational potential energy, kinetic energy, all their initials are going to be equal with their finals there, right? So we can actually extend that particular equation, like the same way we extended it for spring potential energy. Here we're just adding rotational kinetic energy. Then we know that there are certain situations where we are actually going to find ourselves with friction. Okay, so we are going to be looking at something that has got friction, and we know that friction has got what? Friction is a non-conservative force, and so if there is a non-conservative force, we know how we do it. We say work done by non-conservative force is the change in kinetic energy translation, the change in kinetic energy rotation, and the change in potential energy. So it's basically the same things we did in work, power, and energy, but we've just added the rotational kinetic aspect of it. Now, how should you approach problems? So remember, like we were looking at the work energy and this, you always want to have the point of where the thing started from and where it's ending. Initial and final. You need to identify those points. And then you have to ask yourself, what conservative forces am I having here? And then importantly, you have to ask yourself to say, do I have any non-conservative forces? Because if you've got non-conservative forces, your equation is different, right? So you wouldn't want to miss that, right? So that's a key point. Then there are those equations that we've talked about. So you write them depending on whether there is friction, there's a non-conservative force, which is an example being friction, and things like that. Then what you do is substitute the general expressions for the terms. Of course, taking note of certain simplifications where kinetic energy is zero, potential energy is zero, initial, final, all those things, right? And those are things that we exhausted when we are looking at work, energy, and power, right? So having done that, let's see what we can look at. Yeah, so really that's about it. Then now you may have to substitute to use that relationship between translation of velocity with angular velocity. So that's an important expression to take note of. Then solve for the unknown. So here you're then going to use a system of equations, and that's why it's key, it's fundamental that you understand the concepts and not just memorizing. Because memorizing, the moment you get stuck, you can't get unstuck. Then you are stuck. But when you've understood the concept, you can always, work your way around these things. So, so let's do that. So now that's our question, right? So when you look at this question, like we've said, what do you want to focus on? So the things you want to focus on are what. First of all, am I having any friction here? First of all, like we said, before you can even start looking at that, ask yourself, what are your two starting points? So you see, the first, okay, let's look at the question. A ball of mass capital M and r and radius r starts from rest at a height of 2 meters and rolls down an angle of 30 degrees. Slope as in figure 8.27. What's the linear speed of the ball when it leaves the incline? When it leaves the incline. Okay? So when it leaves the incline, what does that tell you? So here is the okay anyway. The incline is this thing that's like a slope, right? So when it leaves the incline, it's basically saying when it reaches down and maybe starts to move along a horizontal surface, isn't it? So then that's that. Then assume that the ball rolls without slipping. So what does that tell you? That tells you that there is no what? First of all, it tells you that of course you can see there that there's no friction that we are considering. So and then the other thing that's important is because the ball is rolling without slipping, we then see that we can then relate the what? The translation of velocity to be equal to radius times angular velocity. Reason being, it's not slipping, so meaning that we can easily rotate because neither the angular velocity nor the translation of velocity is being affected by what? By the sleeping that would happen. But this question, the ball rolls without sleeping, so meaning everything is okay. We don't have any friction, so we just have to start looking at so which equation are we going to use? So we are going to use equation 8.11. So you see, with this done, you see that you realize that these questions are not questions where you should approach them. You are not sure of what's going to happen, but you should be confident, right? Just understand the concept and it will be okay. So we are going to use the equation 8.11. So so here, so it's coming down. So Distance is 2 meters. So then you want to start asking yourself. So first let's write our equation. Equation, translation of kinetic energy, rotational kinetic energy, gravitational potential energy, initial, translational kinetic energy, rotational kinetic energy, gravitational potential energy, final. So like we are doing during work, energy and power, you want to ask yourself one important question, and this is, do I have translational kinetic energy at the top? Because the question is saying the ball starts at rest. So if it's starting at rest, your initial point is here, your final point is here. So is there kinetic energy at the top? No. So kinetic energy is zero. So you write zero. Translation of that is, now this ball is not even rotating at the top. So, and you know you can only have rotational kinetic energy when you've got angular velocity, right? So zero as well. Do we have potential gravitational energy initial? Yes. This object has been raised above the surface. So yes, we have gravitational potential energy initial. Then we now go to the final. This ball is still rotating, right? This ball is still rotating. Okay, so let's first go for translation. This is just the incline. So meaning even when it reaches down, the ball is still is still moving, right? It's just that it has just reached the surface, a horizontal surface. So meaning final kinetic energy is there. That now rotational kinetic energy. That's what the money really is. So what is the gravitational potential energy final? It's going to be zero because this is at the horizontal. Okay, so that's about it. So then what do you do? Potential energy. Now, what is the I? What's the moment of inertia for this ball? So you see, from how this ball looks, right? You can tell that that's a sphere, right? That's spherical. That's spherical. And it's a what? So usually they will actually describe it in a way that will actually help. And that's why usually in some questions they will actually give you the moment of inertia. Cause yeah. But anyway, there we have it. But for this particular ball, the moment of inertia is 2 over 5, right? When we look at that particular uh, diagram that I showed us earlier on. So once you know that, then you are really set. So you just know for moment of inertia is 2 over 5. So so that's that. Then what then now can you do at this point? So at this point you can really make uh, the equation easier. I'm sure you know that we can divide through to get rid of m. Okay, but then more importantly, and where the money really is for us, is on substituting Okay, so what we are having is, remember we talked about this conversion. Okay, so this equation that we are having there, then we say, how can we substitute? How can we substitute angular? So when you square both sides, so you square that. So you see, right? So there you see that that's how we can substitute into that. So what then do we do is how we substitute where angular velocity is. Okay? So that I don't rub what I've written in blue, let's just take it up. So so of course at this point before we can substitute, let's get rid of m. So then we've got GH. So so then we substitute this. So so you can reduce this to 1 over 5. So 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 what you do there, so that's that, right? So then from here now, from what you do then it's, so so then to find this we are going to say, let's make v squared the subject of the formula. So we cross multiply, we are going to have 10 gh 7. Okay, so that's about, okay, actually it should be like this, right? Yeah, so that's that. So from there you just plug in your values. Okay, so that's pretty much how you answer it. And then one thing that you would realize is you remember that we are solving similar questions when we are looking at work, energy, and power. But those questions we are not taking into consideration rotation. And you remember that for those ones, we are finding our equation to be like this, right? But for this one that we found, the equation is 7 over 10 GH. So what do you see there? You see that uh, when there is no rolling or when there is no rotation, you see that if there is no rotation, the velocity is going to be more because all the potential energy that was at the top just goes into translational kinetic energy. But if there is rotation, as in this case, you see that because some amount of energy goes into rotation, that's why you see that this value is less when there is rotation and there is no rotation. So when there is no rotation, it could be something maybe like a block, and those are the questions that we are having, right? When there is a block and things like that. So that just shows that when there is rotation or kinetic energy, the some potential energy will be going into causing the wheel to rotate, and as a result of that, that's why you'll be having those particular differences. Then the other questions which they really like where you've got a block and you've got a pulley. So those are the things that we'll be looking at tomorrow. And once we look at this and we look at angular momentum, then we go to the states of matter. Then we are done with this topic. Okay, so